And before I start, I'd like to acknowledge our partner Intel for co-sponsoring also this conference with us. So the question of what comes after exascale, well, it's not zetascale, at least not for not for a long time. So I mean, we're seeing really at some point that finally the silicon process slowdown is finally catching up with us. So there's been all sorts of discussion in the previous 2 days, and I got rid of a bunch of intro slides because other people have covered that. But honestly, we have line of sight perhaps to maybe a 10x of an exascale system of how it's defined today, but it won't be anywhere near the level of energy improvement that we think. So maybe in 5 years we can see a 10x exascale, maybe a 2x the energy, right? So I know someone's asking for a 1000x energy improvement. That's a far cry from that. And the reason for this is because, as we're getting into the angstrom geometries in silicon processes, most of our silicon partners are telling us, oh yeah, we'll give you 2x performance at 2x the energy, right? So which is great, but not helping much, right? So we think there's going to be a significant inflection, in the generation coming. And we see that really the future is really what we call, and a lot of other people call, system of systems. So we've got to start thinking in terms of, it's no longer going to be the world's fastest supercomputer. It's going to be the world's fastest workflow to enable scientific discovery. And it's not just going to be a massive single monolithic supercomputer. We probably have a little bit of headroom to go maybe one generation, but we don't see a lot more going ahead of that. And the reason for that is because, a lot of us are computer scientists, and we are very centric on thinking that a supercomputer is the center of the universe. I want to give you a sense. This is a picture, an aerial picture of the Oak Ridge campus, and I think I correctly identified, Doug can tell me if that's correct, where Frontier is hosted. And this is, a few miles times a mile or something like that. Now, you might ask yourself, what is everything else? Well, there's everything else, right? So you got light sources, ion beams, material science, metal processing, chemical, irradiated fuels, graphite reactors, biological science, environmental science. So you got, this is really what Oak Ridge is supposed to be, and you can translate that to any other. It's doing science. So supercomputing is in the support of science. And many of these scientific instruments are becoming data generator a lot more aggressively than it used to be in the past. And also, there's an ambition that they're going to become more autonomous in the sense that the instruments are becoming autonomous themselves through AI, so that you're trying to reduce the dependency from the scientists that are sitting next to the instruments to be able to run more experiments. But also the experiments themselves are becoming autonomous with the idea that AI can direct experiments in the right places. So you can imagine that now the requirements in terms of data and workflow of something that you can fast forward 5, 6 years, 10 years in the future of something like this that works a lot more coordinated than it is today are going to really change the nature of the kind of things we do. And so a lot of other people talked about that, but there's if you think about that in the context of an ecosystem, you're going to find that you got a lot of different data types, data sources. You got the very different data patterns from streaming. In some cases, you got urgent computing needs because you got a window of an instrument, and if you miss that window, sorry, next month, right, or something like that. And you're going to have a lot of AI in different places, not just to analyze the data, but to control the instruments, to control the experiment, to do the hyperparameter exploration of what the next experiment should be. And so we really should be looking at this as this is our environment that we're trying to optimize. Now, AI is throwing another wrinkle into the picture. This is the obligatory reference to growth of the AI models. And the only reason I put it up on screen is because pretty much everybody's running out of space in the slides to sort of show the exponential growth of models, right? So if we were 5 years ago and I would have told you that the next model is going to be over 100 billion parameters, everybody would have laughed, most likely. And when we talk to our partners potentially in the accelerator space, what I'm telling them is like, don't make any assumption that you'll be able to hold memory resident models ever. I mean, if you're telling me, oh no, I'll just, I'm going to put 2 chips and it's going to work. It's like, no. I mean, you're going to think about scaling out no matter what you do. Because these models, at least for a while, they're going to go faster than anything you can store in memory. So that is throwing an interesting wrinkle to the whole picture, because now the data is not just your operational data, but it's also the data that contributes to creating your AI models. So here's an experiment for those of you who may not be familiar. When we talked about these edge-to-exascale or extreme scale workflows, I took this again from a team in Oak Ridge that is doing scanning electron microscopy. So you imagine you're studying properties of material, right? So you're on the left. You're running experiments on effectively an electron microscopy, E-beam. You got a computer connect to that. You most likely you have a rack with some GPUs or accelerators that can do some AI next to that. And here are the kind of things you do. A microscope spits out an amazing rate of images. Like, these are not 224 by 224 CAD images. They're like really large images. What you want to do is decide where you're going to do the next experiment. So what this team is working on is using AI to classify the images, identify the atom positions, so massive data reduction, bunch of text, send the atom position to the supercomputer, fire up a simulation of the material in the supercomputer. Think of this like almost a digital twin of the experiment they're doing. The simulation is going to extract the material properties, going to tell you, oh, okay, now you should look, 2 up, 3 left, or something like that to figure out what's going on. So make the decision about the experimental properties, control the computer, and repeat, right? So this is a type of workload where you got a lot of AI at the edge. You had some AI before in the supercomputing to train this model, most likely. You got a closed loop, and you got some form of real time, because you don't want this microscope to sit there idle forever waiting for Slurm to pick up your job, right? So, which is the normal situation today. And the problem is that today, a lot of these things hit a bunch of barriers. Like, there's a lot of execution in silos. A scientist can schedule jobs in the supercomputer, but they got no control on when that gets picked up. So surprise workloads are something that supercomputers don't like. So you get in line and you get picked when you get picked. There's a lot of human interaction in making these decisions. The experiment tracking and reproducibility of something like this is pretty much non-existent, right? Because you don't have a system to record what data you're sending, what is the version, how do you pick this up? It's all ad hoc. I mean, people do that, but there's no real system. And the data staging is kind of a horror, because you normally would like, ideally, to mount your home Lustre file system, but you can't, because you're in a different administration domain. It's literally, you got a different ID. So you have to go through data transfer nodes. So you gotta basically decide, I'm gonna copy the whole universe and then leave it there, and then someone's gonna kick me out, blah, 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 right? So it's really hard. It's really hard to co-schedule things. So there's a lot of complex scenarios that we gotta deal with. Some of the things we may need to solve these are like, and I'm gonna touch on that a little later, is, I need metadata services. Like, similarly, when, today I have a Jupyter Hub server, I got a GitHub server. I want to have a MetaHub server where I can, do a commit of my metadata of my experiment, so that tomorrow, if I want to do reproducibility, I just do, a Git branch, and I get code and data together. I need to have this metadata client and that connect to the data foundation in everything I do. And I need to have some form of an SDK. So what Manish, for example, talked before is the messaging layer of that SDK that enables me to do the scheduling of data movement, that enables me to do the orchestration of co-scheduling between my instrument and my supercomputer, and a few other things. And of course, the network will connect that. So these are kind of some of the things where we see gaps. And in the rest of the talk, what I'm going to give you is a sense of what we're doing, not just at HPE, but what are technologies that need to be developed, what we're doing in HPE, and a sprinkle of some of the things we're doing. So we've come up with what we call 7 pillars for the post-exascale generation of technology. Everything starts, of course, with the programming environment. I'll drive down into each of these separately, but I want to give you a sense of how they're tied together. Everything starts with, again, a programming environment where the scientist and the computer scientist can sort of work together, doing both HPC and AI. then you need this edge-to-exascale orchestration environment, right? So you need to have a way to express a pipeline with different stages that run a little piece here and a little piece there. And there are going to be different domains, right? Don't expect that the same IT administrator is going to control your supercomputer and your rack of GPUs sitting next to your instrument. Then what you need is what I call this data foundation, like the layer of data and metadata that enables me to keep a ledger of what I'm doing so that I can go back. And again, it has to be independent. It cannot live in Lustre. It has to be some different layer, maybe a cloud service or something like that. The computing at this point becomes a lot more heterogeneous in the way in which we were discussing in the panel, because even if my data center is homogeneous, then I can see on the edge having specialized devices that are tied to the kind of things I need to do. Or if I'm on an electron microscope, I need to do imaging. If I'm on a particle accelerator, I kind of need to do imaging as well. But there's other domains where I need to do different things. So I'm going to have different accelerators that are tied to the environment. Your data layer, the storage layer is also going to have to be different, right? We're kind of used to this monolithic, gigantic file system, parallel file system that work really well with HPC, but again, they become clunky when you need to access them from the outside. So now we're talking about capturing abstractions like object stores or different type of pipelines, things that are more native to the AI environments that don't really speak Lustre or GPFS. And the network is important because now, again, we have developed amazing networks that do very fast RDMA-type protocols on HPC, but they're kind of hard to port to a more of an edge environment or even a federated environment spanning two different parts of two different data centers or two different supercomputers. So there's something in the networking. And the last thing is security, and we touched a bunch of that in some of the previous talks, but clearly there's a level of security that goes simply as how do I identify myself in running these workflows? Do I need to go towards more of a token-based authentication, which is more natural to microservices and cloud? And who enforces that? Where are the certificates and so on and so forth? So these are what we think are the 7 pillars that are important to be developed. We're not doing all of them ourselves. Again, I'm going to touch on some of the things that we think are important in each, but we think it's very important to think in terms of the system of systems and in kind of these 7 dimensions. So let me start with performance productivity. Clearly, we are mostly familiar with the HPC world. We got tools like the Cray programming environment that worked really well for a long time. This is sort of a familiar environment. You write things in your combination of MPI plus X, and then you send them over to cluster, share, and resource management. Well, AI comes into the picture. It does complicate a few things, as you show in this picture. Because now someone's trying to build a AI plus HPC job. First of all, you got to deal with different frameworks. It's TensorFlow, PyTorch that are kind of the two big gorillas in the field. You got to do with data prep and ETL, because now you got to deal with training your models before you can even start using it. And then you got to start doing things like, okay, I need to do hyperparameter search for the model. I need to do perhaps a neural architecture search to figure out the shape of the model itself. Then I need to stress test and debug the model because these things are kind of brittle in many cases. I want to do that in parallel and distributed training. And I want to track my experiments and keep all the metadata layer. And by the way, I need a model registry to then publish my model so that someone else can pick it up. So these are all kind of foreign technologies for the HPC and science world. Some are becoming more familiar, but a lot of these are new. And for example, as a company, we made some investments in acquiring technology, a company called Determined AI. By the way, everything that I'm talking about here is primarily open source. All these things can be picked up from open source communities. We have, of course, supported versions, but all of these things were, we believe in these things being community-driven more than proprietary. So Determined AI, for example, gives you a tool that we're integrating very closely with some of the HPC environments. Pachyderm is another company we acquired recently that gives you data versioning for reproducibility. So now you can do it, as I said, you can do a Git clone and get the whole version of the data and the pipeline that's tied to that data. And then, of course, once you've created your model, you got to deploy it, right? And you can deploy it at the edge in the microscope experiment, or sometimes you want to deploy it in the loop of your simulation. Stop every few time steps, take a breather, launch your surrogate models, fast forward to a certain place, or around the loop and all the other mechanisms people are looking at. So this is not easy because you got an MPI job running over, ideally 10,000 nodes with like some hundreds of thousands of ranks, and in parallel you got an AI stack that's written in Python and expects a completely different parallelism model, right? So what we've been doing, for example, with the project, it's also open source, called SmartSim, is try to couple those two worlds through an in-memory database. We're using a flavor of Redis, where effectively from your MPI world, what you can do is make a call and say, here's the state I want to pass to the inference. Then from the Python world, what you can do is you pick up that data when you want it, run an inference on your model, and then communicate the results back. And that gives you a way to effectively combine the two worlds without kind of forcing them to marry each other, right? Because we know that the AI world goes at its own pace. It's driven by most of the cloud. In the HPC world, yeah, well, good luck trying to find someone who write things in Fortran and tell them to move to Python, right? So, there are kind of practical solutions to that. This is not the only one. There's others. I think Livermore's got something called Merlin that does something very similar. But there's solutions that need to be thought carefully on how you do that without losing performance and enabling all the type of, in the loop, around the loop, or outside of the loop kind of AI connections. So the edge-to-exascale orchestration, I'm going to go probably pretty quickly because we heard a lot of that. And again, the things we're trying to do here is identify different patterns, right? We got the heavy edge, which is the experimental facilities edge that I mentioned. There's also the light edge, some of the project, for example, that Pete is doing with, Sage, that is thinking more of a, really edges in a distributed over the territory with much smaller devices in a smart city. And both of them, you need to be able to capture kind of the patterns that people want to implement in this workflow through what I think is a need of the community, which is a set of APIs and SDKs that would enable you to write these workflows. Now, as you probably know, and there was a good paper that showed up maybe last year that talks about there's like 438 workflow engines in this community. I think that there's the joke is that there's like 1.5 workflow engine per developer. And so, I'm not proposing that we solve this by creating workflow engine number 439, but at the same time, I would like to create microservices that these workflow, and by the way, in many reasons, these workflows were created for a reason, right? Maybe not all of them, but because you have special needs when you are doing something in a certain environment. But I still would like to offer microservices that are more common to name things, to identify yourself, to describe how I co-schedule something, to pass the information to different schedulers in different places so that it's no longer a surprise workflow, but it's like, oh, I'm planning for that, right? So how you do the data transfer without mounting the Lustre home directory. So all of these things are going to have to be important, and I'm trying to capture some of the properties here to managing the life cycle, doing the metadata layer and so on that I think are going to be necessary one way or the other. I'm really glad to see some efforts that are going in that direction. The data foundation I mentioned, I think is very important. Again, there is a gigantic gap today between the AI frameworks, the PyTorch, but also, think of MLflow, Kubeflow, all the places that you kind of use to kind of describe your machine learning workflow, and then your storage system where you just dump the data, right? And so what we call this data foundation in the middle is the set of tools and, again, microservices that help you bridge the two. So you can describe, when you're doing some transformation in an AI pipeline, what data you touched, how you version it, who has touched that. And so this helps you do things like detecting drift when I'm deploying a model and being able to go back and say, oh, I need to retrain it, but maybe only for a subset. And again, there's good technologies out there. We started in labs with something called DVC, which is a data versioning tool, open source as well. Then, we decided to acquire Packard, which would be a replacement of DVC. But we think what's really novel in this environment would be the self-learning component, because once you observe some of these pipelines, you can learn from previous execution things you're not doing well. The obvious one is, for example, tiering of data, right? If you understand how fast the GPU is consuming your data, and you can inform your data tiering system that you only need to prefetch that much, right? You don't need to, prefetch too much, because, the GPU is not going to be able to consume that. And if you don't prefetch enough, then the GPU is going to be sitting there doing nothing, right? So these kind of things you can learn, and then you can inform your system to do that. Something else that is interesting, and we've done some experiments, for example, on ClimateNet, is on what we call the northbound intelligence. Like, can I help create a better training workflow? And for example, in many workflows, when you're creating models, your bottleneck is not the training time, but is the labeling time, right? And the reason for that, for example, in this case, we're using ClimateNet or some cosmology data sets, because your labeling time requires a PhD in cosmology to look at an image and figure out there's a black hole or who knows, whatever it's picking. I mean, they show that image to me as just like a bunch of random pixels. I don't understand it. So, labeling of that image is really expensive, right? Because it's a highly trained scientist that needs to label that. So you don't want to do the brute force approach of labeling everything. What you want to do is use, for example, an active learning training flow, where it's like the teacher-student approach, right? So you start to train, you break your training set in little chunks, you start to train, you do UQ, uncertainty quantification, then you say, okay, I need more of this, so give me a data set that has these properties, a data slice that has properties, and then I train more, right? So it's like the students say, well, I don't understand integrals, give me a few more examples, and the teacher's gonna say, oh, here's a bunch of tests you can do. And this, if you think about implementing that kind of a active learning flow, you need a lot of the microservices I just described in the data foundation to even be able to consider that. And now in that case, the advantages are massive, right? And even for the simple experiments we're doing on ClimateNet, you can cut down the labeling cost by 2x. So you can basically only label, half for your data set and still get very close to the same accuracy if you label everything, right? In addition to saving like training time if you do it correctly. So there's potential for doing a lot more of these kind of things. So heterogeneous computing, again, I'm not going to spend too much time on that, but I see, and I talked about that yesterday, heterogeneity really going more across the spectrum, where the edge is going to have something very different than your specialized system. I know many of us, I remember, I think with Jim and I were running ICRC, we're giving all the talks about the Cambrian explosion, right? That was, what, 5 years ago, 6 years ago? It's gone on, COVID in the way, of course. It was a season, yeah. And with my friend Cliff Young at Google, we were chatting on a side during Hot Chips, and we came up with a term that's called Ordovician casualty. And that is, for those of you, at the end of the Cambrian period, there's something called Ordovician period, or Ordovician era, that was basically a mass extinction of about 75% of the species. And I think we're kind of getting there. There's been a little bit already, like Mythic has gone belly up, some of the other big players are kind of starting to struggle, and the reason for that is because it's a challenge, right? And a lot of people, if someone tells me, if you're folding the origami in a different way, where the origami is your combination of digital logic and gates, there is not that much you can do, right? So you got to really start thinking about some of the novel technology, and we heard some of that. in the last couple of days, like some of the neuromorphic analog computing. Those are really the ones that will give you the breakthrough that's needed. Unfortunately, they're hard to find the space for. But I think that there's a lot of heterogeneity kind of hype that's kind of getting into the trough of disillusionment. And it's going to come back up. But right now, especially with the macro financials, it's getting challenging. So one of the things we're doing ourselves, for example, is working on analog in-memory computing. Our favorite stack in this particular case is a resistive RAM technology. That's a derivation of the memoristor work we've been working on for the last 15 years. But now we're trying to apply it to, for example, decision trees. We think that there's a branch of machine learning that is very good to do things like, for example, what Jeff was describing. If I have a particle accelerator, I gotta classify very quickly, low latency, the particles in like good, bad, need to pay attention to or something like that. Then things like random forest, which are kind of ensembles of weak learners, are really good at that because they're also predictable, explainable. And so it turns out that, for example, they map extremely well to an array of CAM cells. CAMs are content addressable memory, except we do them in analog. So imagine that every CAM cell of a big array of memory, millions of cells, can do effectively 2 floating point comparison and an end. So it means that it can spot whether the incoming feature fits between a range of 2 values, right? So by doing a little bit of simple compilation technology, we can map really complex decision tree into these cells. You map the root from the leaf to the path from the leaf to the root, and that becomes a column of your array. And effectively, in one shot, in one cycle, you do all the comparisons of this tree, right? So there's no GPU on the universe that can do that because GPUs tend to be really bad at if then else, if then else, if then else, right? I mean, you can force the tree to be fully balanced, but you're cheating. But in general, this is, we're seeing that in terms of latency, this technology gives you, a nanosecond, hundreds of nanosecond latency. The GPUs are in, tens of microseconds or milliseconds in some cases, right? So, there's potential in these technologies to be applied in different ways, and this is not the only one, of course, but I think that really the heterogeneity, we should be looking at some of these things, and this could be perfect as next to an instrument if I need to do really fast, real-time, like classification of a lot of, events. Last 3 things I'm gonna go quickly here is data accelerated storage. Again, we've been used to the world of Lustre, effectively, or parallel file system for a lot. As you think about these workflows, they need to be multi-tenant. They need to combine AI accesses. They need to combine analytics and compute. Some of these file system abstractions are starting to break a little bit. Now, of course, you still have people that want to use them, but we think that there are better ways to do it where those parallel file systems become an abstraction on top of something that is more scalable intrinsically. So for example, a project we're working with Argonne and Intel is something called DEOS, which is at the foundation a distributed object store based on commodity. So it can really spread out, doesn't need any funky RAID hardware or things like that. That's becoming a little obsolete. But you can layer on top the abstractions you want. It could be a parallel file system, or it could be an object store, or it could be something that extends to the edge because it has built-in tiering and manages multiple namespaces. So we think that's a good direction. And again, there are different projects out there. This is the one we like because we've been investing in it. But again, that's sort of a direction. Last 2 things I want to mention is network. I know that, as a company, especially after the Cray acquisition, networking is one of our cornerstone of HPC technology. There are a few things that we want to do. We want to make sure that we can extend the HPC paradigms to the edge, right? It's not impossible because, you can do effectively L2 bridges encrypted with the right properties and then possibly extend RDMA into other dimensions that are not only your supercomputer. You can also think of blending some of the supercomputer and cloud directions. Again, when I'm thinking about this workflow in a federated environment, now you got a lot more, properties that are coming from the cloud world, like isolation of multiple tenants. You're talking about QoS. You're talking about, potentially a single job that's touching 1,000, multi-tenant instances or stuff like that. And last, we're noticing that there's a growing interest in the HPC functionalities across the industry, including the hyperscaler world. So there's one dimension that is, of course, we're cloudifying the supercomputer, but there's a lot of the hyperscalers that are also supercomputifying the cloud. I'm borrowing this from, I think, Satoshi's recent paper. And so, people want to run RDMA, they want to run offload, they want to run isolation, they want to run all the stuff that we do well in HPC. And so there's an opportunity here to kind of try to use, Ethernet. Slingshot happens to be Ethernet compatible, performant with the right congestion control and multi-tenancy. Very last, security. Well, security is important, and in some cases, it goes way beyond what people think about. For example, one of the areas where we're really seeing a lot of issues is in the supply chain, right? In the sense that, we're relying on supply chain that has a lot of unknowns, and we run the risk of getting free parts, as we call them, right? So parts that you did not ask for in your boards that happen to do things that you may not want to know. And so, to do that, there's a lot of stuff that needs to work through the entire supply chain, including, attestation, making sure that, everything, you got a manifest of all the parts. If one part is not in your manifest, it's a bad thing, right? You want to have authentication, blockchain, in making sure that every step of the supply chain, distribution, and manufacturing goes through a process, right? It's scary because some of the security folks tell me that today, the advanced persistent threats are like when someone sneaks into your network, it's like an uninvited guest at home, and it takes you over 100 days to find you got someone at home that you don't want. I mean, it is scary. And actually, I think the number's going up. This was 2018. I read a report from IBM that's gone over 200 these days. So. And why? Well, somehow they get in. So how do you do that? I mean, you need to do scrubbing of kernel traffic. I mean, there's a lot of stuff you need to do. We're working on some of that. Some has gone in production. There's a link here in Project Aurora is some of the research we're doing. But I want to make sure that, people realize how critical that is, and especially now you're crossing administration domain. You got stuff in the edge, which is physically, under attack and all this kind of thing. It's not just the identity. It goes a lot more. You got to go in and look at your supply chain and things like that. I want to wrap up. I mean, again, I think that there's a disruption coming. We're already noticing that. That is, and this is one of my favorite quotes, that, we know that AI will not replace the scientists, but I'm pretty sure that the scientists that know how to use AI will replace those that don't. And so it's becoming one fundamental tool in scientific discovery, including HPC. And we see that these complex science workflows are going to touch a system of systems. They'll span all the way from the experimental edge. And we think we're observing probably the last generation of monolithic supercomputer. It may extend a little more, but I don't see us building one exascale supercomputer, zetascale supercomputer anytime soon. I mean, we will have zetascale capabilities, but it probably is going to look very different from what we have today. It's not going to be in one room with 100 megawatt going into that, or 200 megawatt going into that. And so we really think that the next breakthrough will come from formalizing and developing technology that touch this system of systems view. And with that, I think I'm done. Almost in time.
Thank you very much.
Man, it's getting hot here.